Thank you very much for the invitation. It's really good to be here. Um, so as you said, I'm going to be talking about additive combinatorics to infinity in the presence of a lattice, and this is joint work with a grad student at Stanford, Spencer Dembner. Okay, so the setup is going to be this. Let's say I have some set in R to the n defined by polynomial equations. You know, like a circle or a line, or maybe like a higher dimensional thing. And we're going to let lambda in R to the n be some discrete subgroup. So like z, or like z squared, or like for the purposes of, you know, thinking about what's going on, you can basically think of like z to the k times 0 to the n minus k, and no generality will be lost. And we have a map that takes r to the n to the quotient of r to the n by this discrete subgroup. And the question that I'm going to be looking at, and which I will subsequently motivate, is the very broad and probably impossible question to study, which is what can we say about pi of x? Yeah, so x is a nice set. Discrete subgroups are, you know, reasonable. You consider the quotient. Now somehow this nice algebraic set is interacting with a lattice. And like a lot of scary things can happen when an algebraic set interacts with a lattice, because now you're getting into like Diophantine questions that might determine what points are in this projection. Because if, for example, x can approximate certain points, you know, the fractional parts of certain points, then you're going to see that if you quotient by like z to the n. And like whether certain points are in this set is, you know, a Diophantine question, which is very scary. So let's look at some examples. So I'll draw some pictures. So let's first look at r to the 2 mapping to r to the 2 mod z to the 2. And let's see what this set looks like in 3 illustrative examples. So here I have r to the 2. I'm going to draw a fundamental domain for this quotient. So you can imagine that I've like tiled the plane by these squares, and then the image is going to be like I take a snapshot of my variety in each of these squares and then just superimpose them all onto a single square. So for example, if my variety is just the circle, then pi of x doesn't do anything scary. It just returns, you know, it just returns the same circle. So here I would have my model of r to the 2 mod z to the 2, which is a square with opposite sides identified. And we would just see the circle. So here, pi of x is nice. And like, there weren't even any new interesting points that were approximated in the limit. So it's actually equal to its closure. And this will generally happen if you have like a compact subset of r to the 2. You know, this map is going to break it up into finitely many pieces and superimpose them, but it like preserves algebraicity because each of those pieces is algebraic and you're just translating them and moving them over. So, you know, if it's compact, nothing interesting happens. You know, it takes algebraic sets to algebraic sets, everything's fine. Now let's look at a more interesting example where something goes off to infinity. So here, I'm going to take a hyperbola. Also, if anyone has just any questions, I'm I can just stop. I've budgeted like plenty of time. I'm not gonna get close to running over. Right. Here's my fundamental domain. And now it actually matters that the fundamental domain is tiling the plane. So when I consider, we demand that X to have the symmetry of the subgroup lambda. No, X is just some random thing that might not interact with the lattice in any useful way. And actually, if it, depending on how it interacts with the lattice, this is actually a very subtle question of what the closure is. So I'll give an example of that maybe. So here, if I take this parabola, then what's it going to look like? Well, what we see in the current square looks something like this. And then like as this point here, as we enter the next square, it comes out the other end like this. And then we can like see it approaching some line. So it approaches the x-axis. But it never touches the x-axis. And similarly, as it goes up, it goes this way and approaches the x-axis. And it does that on both sides. So similarly, the other arc of the hyperbola, comes in and approaches both of these lines from the other directions. Okay, so what does this example show? This example shows that pi of x is horrible. So pi of x is bad. The set of points that we're not in, that pi of x approximates, is then also bad because I didn't add in too many approximating points. However, there's a very nice set that we added to pi of x to get the closure. So these are the new points that you can approximate with points of pi of x by like this sequence going off to infinity, but are not themselves in pi of x, and you get this nice union of two lines. So this is a nice, I guess if I were to describe it in a sophisticated way, I'd say this is the union of two compact subgroups. Subgroup, let's say cosets of r to the 2 mod z to the 2. So super, super nice. Super nice. Even though we had a bad set that obviously I tried to draw it and it had a bunch of scary features, this like stuff we had to add into closure actually turned out to be pretty nice. Okay. So now to go to answer Vladislav's question of, I guess the general question was, does it matter how X is positioned with respect to the lattice? It actually matters quite a bit. So for example, if we rotated this example by an irrational amount alpha, in like, so if we rotate it by some like random amount, then the like asymptotes would fill up the square, would fill up the square, because they would like wrap around in like some irrational way, and then you would see these lines like wrap and wrap and wrap and wrap, and it would like densely fill up the square rather than like limiting to these two nice things. But you would still have the property, I'll note, you would still have the property that even though pi of x is bad, I guess pi of x bar is super nice because it fills up the square. like you have this like line is tilted irrationally, wraps around, fills up the square. Pi of x bar is just the square. So we can say that as pi of x bar together with the entire square, sorry, pi of x plus the entire square, I guess union, is equal to pi of x bar. So there again, we have this feature that the new things that we add in due to the asymptotic behavior of the set turns out to be nice. In this case, it's like nice trivially. And this also happens even for like a set where the limiting tangent is actually in the direction of the square. So for example, if I take a parabola.
So wait, you take the limit points that are not in the set, and then you take the closure of that again, or what?
So here I'm just writing down a true statement. I'll formalize like what the point that this new set is like basically pi of x bar minus pi of x. It's just like the complement, like what I need to add in, except I'm going to make a definition that makes it clear that that I'm going to make a definition which like isolates specifically the entire square rather than because you're right, because the difference between pi of x bar and pi of x is actually something rather terrible. So I'm being rather sneaky by taking a union rather than a disjoint union. So that's actually important for me, because if I took the disjoint union, I just get the complement and that'd be terrible. So that's actually important that this is just a union for my purposes. Right. Okay. And I'll draw an example where this is happening. So here we have the parabola, and basically what's going to happen is we get the parabola, and then what's going to happen is parabolas grow faster vertically than they do horizontally. So very quickly, the snapshots are going to look like vertical lines, and they're going to have some like slow drift along the square as I go off to infinity, with the slowness of the drift being because it's growing faster vertically than horizontally. And these like lines are just going to densely fill up the square in both directions, I guess. So then the points that are limited to by these lines is everything. Every single point gets arbitrarily close to one of these lines. So we have, again, a similar situation to what I was describing with the hyperbola, where pi of x union the entire square is equal to pi of x bar. Okay, so with these three examples in mind, I'll tell you my theorem with Spencer, and then I'll tell you like why, like what the main application is and how it connects to, like why would anyone consider this question. So probably put these in the wrong order alphabetically. The closure of pi of x is equal to pi of x together with a finite union of parametrized families of I guess subtoruses. So these are compact subgroups of r to the n mod lambda, and these y's are smaller dimension than x. And this is basically best possible. So there are examples which show that basically no feature of this description can be omitted. I guess in the case that x is a one-dimensional curve, this is saying that the closure indeed has this property that you can add a finite union of like coset translates, because now yi has to be 0 in order to get the whole thing. So here we had to add the square, 2 lines, and nothing. So they all satisfy the hypothesis of this. They all satisfy the conclusion of this. Okay, so why did we prove this? I mean, it's a nice result, and ultimately it's related to the interaction with how your set is like, what your set's behavior at infinity is relative to this lattice. So there's going to be some interesting additive combinatorial questions. But the application has nothing to do with additive combinatorics. The application has to do with the following situation that people have considered quite a lot recently, related to questions of functional transcendence. So a big research program asks, like, how do transcendental maps interact with algebraic sets? That's a big research program. So let's say that I have, for example, the exponential map, the coordinate-wise exponential map, Zn to x of z1 dot x of Zn. Then a very classical theorem describes how X preserves or doesn't preserve algebraic relations. So basically, the Ax-Lindemann-Weierstrass theorem says X preserves only one type of algebraic relation. And I'll phrase it in a way that makes it very similar to the question that I was studying. Okay, so for example, let's see if X preserves any algebraicity when applied to the parabola. So you apply X to this parabola, and you get the following set, where it's confusing that you have to use the inverse of a function when you describe the image of a set under something, but whatever. So it's this, which is equal to like the set of all v and u, so that v lies in e to the log u squared plus 2 pi I z, I guess. Okay, so this is obviously some like horrible, this is some horrible non-algebraic set. There's no algebraicity with this curve at all. It's just some stupid thing I wrote down. On the other hand, X does preserve some types of algebraicity. So if I have, for example, linear equations with integral coefficients, there's this very nice fact that that log turns addition into multiplication. And what you get is that if I take an integral linear subspace, then you end up with a algebraic subgroup of C star to the n. So that's preserve algebraicity in this case. And in general, how the like sophisticated way of phrasing this is that understanding what algebraic relations that X preserves is basically equivalent to asking what is the smallest algebraic set that contains X of X. So if it grows a lot, it destroyed a bunch of relations. If it doesn't grow at all, it preserved a bunch of relations. So like how much you had to grow is basically saying how many algebraic relations are preserved. And the theorem says that this is a union from I equals 1 to k of finitely many subtori. So in this case, these are algebraic subgroups. So basically, if you take the image and then you want to grow it in the minimal possible way to be algebraic, you're basically going to end up using these examples here to like just cover your set in kind of a coarse way. That's the only way that you can end up getting something algebraic, to squeeze an algebraic, blood out of this transcendental radish. Okay, so let's see a corollary of the theorem that me and Spencer had in the context of the exponential map, which is why we bothered to study this question. We get that the exponential map closure is equal to So in the topological sense, the closure, which is intermediate between the thing and its Zariski-closure, is this horrible set that you would never expect to be described in a reasonable way, x of x. But the new points you have to add are parametrized families of, so these are lower dimensional semi-algebraic sets. So even though I started with a complex algebraic set, the parametrizing set genuinely sometimes has to be semi-algebraic. And these TI are compact subgroups of C star to the n. So you end up with a situation where surprisingly, even though X is complex analytic and you start with a complex variety, the real numbers actually do come in. There are examples where they're required to come in. All of these things, like I can't improve any part of the statement. This is like the best possible description. You can actually get real tori, even with a complex curve. When I consider the image of the exponential map, you actually can get real subtori. And the reason is basically like if I have a complex curve, so if I like imagine some like complex curve in like, C to the n, then like at infinity, this is going to only have finitely many branches. It's going to like do something crazy in the, bounded part, and then it's going to go away and do something predictable. And you're going to see that the set looks more and more like some complex plane. But the problem is that the image of this tangent plane under exp is a real subgroup of C star to the n rather than a complex subgroup. And the reason is basically because like Z to the n, right. So I have to say like why this corollary is implied by a result is just because X is topologically the map C to the n to C to the n mod 2 pi I z to the n. So you just directly apply a result. Right. So the point is that if I consider this complex subspace inside this quotient, somehow because this lattice you're quotienting by is not invariant under I, it actually destroys the property of being complex. If this lattice we quotiented by was stable under multiplication by I, then you would get complex subspaces, like subgroups of you would preserve this complexness. But because it's just some random lattice relative to the complex numbers, you actually do just get some random thing that happens, similar to like how an irrationally slope hyperbola will just randomly fill up the entire square. So that's why the real numbers are coming in. It's basically because topologically the lattice you're quotienting by is actually a random lattice with respect to the complex structure on the complex numbers. Great. So any questions about this so far? Okay. So how did we do this? Well, what we did was the following thing. We adapted some other people who did something much smarter than us. So Pierzo and Starchenko used model theory to solve this problem when lambda is co-compact. So if this lambda had like the dimension of the lattice was equal to the dimension of the ambient vector space you're quotienting by, so you get a compact thing, then this is no. So for example, those examples I drew all fall under the regime of something that appears in Lensarchenko already solved using model theory. But it was thought that you couldn't really adapt the, what they were doing to the non-co-compact setting, which is super important for us because if we want to apply it to a situation like the exponential map, then we need to do that. So for example, they could apply their result to like the exponential map on an abelian variety. And now we basically lifted that restriction and we can consider the much more natural exponential map on like just, the usual exponential map that everyone, knows. Right. So basically model theory is scary. So I'm gonna like extract the interesting, like surprising additive combinatorial property that algebraic sets have. That is like maybe one of the more surprising things I've ever seen in my life. And it just falls right out of their theory. And getting like this specific result is like a little fiddly, but getting something that's like very close to this is actually super easy using their technology. So that's what I want to like describe to you in the last part of this talk. Right. So the idea of the proof is instead of considering everything in the image of pi, we're going to consider everything in the domain and then project to pi. So if I can solve this equation, y union x plus lambda, then applying pi, I would get the closure of pi of x is equal to pi of y union pi of x. So basically, I want a nice description of a set y, which has this property that when I union it with this rather horrible looking set, I'm taking my algebraic set and I'm taking the union of it translated in all possible ways according to this like subgroup. I want to like cover the stuff between that set and its closure. Okay, so let me make some notes. So as I said before, we don't want to take it to be the complement because taking it to be complement in the case that x plus lambda is, for example, everything, would end up with some scary set. And we don't want a scary set. We want like a nice set. So here's the observation. So x plus lambda. So, x is some closed subset and lambda is some closed subset. So x plus lambda is equal to the closure of x plus the closure of lambda. So I'm going to write x plus lambda in kind of a tortuous way as the limit, as all limit points xi plus lambda I, where xi in x and lambda I in lambda are both bounded sequences. So sometimes this limit exists, sometimes it doesn't. When it exists, it goes in the set. Obviously I could have just said the set of all x plus lambda such that x lies in x and that lambda lies in lambda, but I'm going to do this for parallelism, which is great. All right. Now I'm going to write down the definition of x plus lambda closure, which is going to make it clear why I bothered to do this thing. So x plus lambda closure is the set of all limit points of xi plus lambda I, where xi in x and lambda I in lambda are arbitrary sequences. Okay, so hopefully I didn't say anything too contentious so far. But now I can define what I want y to be. So instead of y taking it to be the complement, I'm going to take it to be the set of all limits of xi plus lambda I, where xi in x and lambda I in lambda are unbounded sequences. So it turns out that just by restricting to the set of limit points that occur from unbounded sequences, you actually end up getting this nice set. So somehow by taking unbounded sequences, this definition is not sensitive to like any finite part of either X or lambda. And as a result, it like removes all the grossness of, for example, the parabola filling up the square, and just leaves all the nice limit points, which is the the square itself. So like any particular point that I drew, like while I'm filling up the square, all of those particular points get removed. It's only the limits that actually stay, and the limits are nice. So this is, based on the pictures, a reasonable definition. So I guess I can make a more general definition. The frontier set for Z of X, let's just define this to be this unbounded sum sequence thing. So Xi and X, Zi and Z, unbounded. So I can really define this for any two sets. It doesn't have to be like an algebraic set and a lattice. It can just be any two things. Okay. And I guess the observation was that, X plus lambda bar is equal to this frontier set union X plus lambda. And just so I can make it like maybe a little bit more clear that this frontier set is doing this thing that I'm saying, let me note that the image of this frontier set is literally the big intersection of all things you get by taking pi of X minus a big ball. So in the case of a lattice, if I consider this quotient, basically the set is what I get when like pi of X is like a really scary thing. And basically I'm removing more and more of pi of X. I guess I have to take the closure. So do I have to take the closure? No. All right. So, okay, whatever. And it doesn't really matter. I think I motivated this enough. Okay. So this frontier set is the interesting thing. And how do we access this frontier set? So it turns out that there's the following amazing theorem. So you might think, okay, obviously I'm going to use properties of a lattice in an essential way to prove this theorem. And in some sense, you do need like some property of this lattice to even state the theorem, because otherwise this like projection map doesn't make sense. Put in this form, I guess it's a rather strong property of what the frontier set looks like that's being described by this theorem. But if I want like a slightly weaker statement than like the full statement that I had in the theorem, you basically need no properties of lambda, are used. So here is my surprising theorem that follows from model theory, that the frontier set is always a union of lines. So this is kind of surprising, because what it means is that in order to cover the closure of X plus Z, where Z is any set, literally any set. So to cover the closure of X plus a set, it's a bunch of lines together with X plus Z. So the relevance of this, of course, in the context of the original question, is that when I take the image of a line under this projection map, it's going to end up like wrapping around this, square that I drew, and it's going to fill up one of these toruses, one of these like compact subgroups. So the compact subgroups are arising as like the images of these lines in this beautiful description of how you add, this algebraic set onto just any set. Doesn't have to be a lattice. So no properties of the lattice are used for this slightly weaker statement that would, that is what I want to focus on, because this is already, I think, the surprising thing and has like the key idea in it. Great. So this obviously has to be a very strong property of X, the algebraic set. So this is the algebraic set. So obviously something about X has to be important in this thing to get such a strong like property of addition with respect to any other set. The key basically is going to be that algebraic sets, and more generally this class of sets that model theorists consider, which are called O-minimal sets, like as you go off to infinity, they like have asymptotic behaviors. So for example, in this, for curves, it's kind of intuitive that like as an algebraic curve goes off to infinity, the like tangent spaces like limit to a certain direction, and then that direction becomes like a line. So when I like ignore the bounded part of an algebraic set, I get things which are like, if I look like way off to infinity, everything kind of looks like, like a line, or in higher dimensions, it's going to look kind of like a variety times a line. It's going to look like something that's stable under addition by a line. And it's this property of the set at infinity, like really far away, that is going to make it so that we're able to prove such a statement that the closure of X plus Z is a bunch of lines union X plus Z. So yeah, let's see what how the model theorist would phrase this. So we have the complex numbers, and then the model theorists do something called taking a large saturated extension, which I guess I'll call C, written like in a crazy way. Actually, I'll write like a curly C because I can't draw that fast enough. So C. Okay, so this is like this is another algebraically closed field. Well, non-algebraically closed field. We're basically going to forget. So we're going to forget all. I guess the complex numbers no longer play any role in this. So forget all things about complex numbers, because they play no role in this about complex numbers. So this is really a real statement of like sets inside R to the n. So I take R and I take a large saturated extension. Now, intuitively, we should be thinking of this large saturated extension as, so like R contains points, and this large saturated extension, the intuitive idea is that we should think of it as containing sequences of points in R. Okay. So, sometimes sequences go off to infinity, so you get some like really big points. Sometimes sequences converge to something, and then you're going to get like points in this R, which are modeling like how fast those sequences are converging to a point. Then you get some random sequences that don't do anything interesting. Okay, so here is the thing. So for every subset X inside R to the n, we can produce this set X sharp inside R to the n. And like, again, avoiding all model theory, this should be thought of as sequences of points in X. Okay. Now, R to the n has three important subsets: mu to the n, O to the n, and R to the n. And these should be thought of as sequences converging to 0. So these are the infinitesimal elements we add in. O to the n are sequences converging to a bounded thing. So O to the n is like mu to the n plus usual R to the n, where usual R to the n is embedded through constant sequences. So to get any bounded sequence, I add the constant sequence to like a sequence that converges to 0. And then R to the n, this fancy R to the n is like all sequences. Cool. Okay, so now here is the logic that you go through to prove this amazing fact. And at one point, there's going to be an amazing theorem that goes behind the amazing fact. Right, so I want to study the closure of X plus Z, where again, Z is just some random set. Okay. So one more piece of notation. I'm going to define the standard part map of O to the n to R to the n is the limit of the sequence. Okay, so it drops this mu to the n part and just remembers the R to the n part. Cool. Okay, so first, the closure can be described using this framework as the set of all, so the closure by definition is the set of all limits of sequences that lie inside your set. So I can write this using all of my crazy notation like this. This is just a direct translation of the closure is the set of all limit points of sequences in the set. I guess I should really intersect it with, sometimes sequences don't converge. Cool. Okay, so now a sequence in a sum is just a sum of the sequence in each of the individual sets. Cool. So again, nothing scary has happened. Model theoretically, this is where I use saturatedness, but whatever. I'm working with sequences of points, so it's not rocket science what just happened there. And now I want to split this up into the bounded sequences and the unbounded sequences. So we have on the one hand that this set of points, you're either getting a set of points from each of the sequences added together that were bounded. So you either added two bounded sequences together and took their limit, or you added two unbounded sequences together and took their limit. So maybe I will write this as like X sharp intersect R to the n minus O to the n plus Z sharp intersect R to the n minus O to the n. So this thing, if I add a bounded sequence in X to a bounded sequence in Z, this just recovers X plus Z. Oh, I guess I need Z closed. My apologies. Z is closed. Okay, so because X is closed and Z is closed, you get X plus Z. In general, you get like X closure plus Z closure, but whatever. Right. So this is the interesting, this is the frontier set that we're interested in. We want to say something about it. And at the moment, I've just pushed around a bunch of symbols. So, there better be some, really great thing that happens. And there is. Okay, this is what happens. So what we're going to do is we're essentially going to stratify the set into parts according to this thing here. So we're going to take all sequences that lie inside X that go off to infinity. We're going to partition them basically under the equivalence relation of algebraic indistinguishability. So like if two sequences can't be distinguished by in some way by some like algebraic formula or semi-algebraic formula, I should say, since we're working with the real numbers, then we're going to like group it together. And this is what model theorist calls a type. So we're going to go a union over all types alpha of types alpha contained in X, which are unbounded of the following thing. So alpha is like some scary subset of scary R to the n. So we partition this into alpha plus, I'm just call this W. All right, so here W doesn't matter. It's just something. Okay. So the key thing is that these alphas came from this procedure of like we partition all of X into algebraically indistinguishable subsets. So for example, some of the types of X are the individual points of X themselves. But then like there are other points of X that you can get by, for example, some other types that you can get, for example, by considering they're like these types at infinity that come from all these like fun infinite points of X sharp that exist that didn't exist before. So for example, with the hyperbola, there's like a point at infinity that was added in. And more generally for higher dimensional sets, they're going to be like whole like subsets that are indistinguishable. But for curves, it's really easy. There's just like one point like modeling, like I'm really far away at infinity in this direction. Great. So now Pirzil and Starchenko have the following result, which is the theorem of infinitesimal stabilizers. Theorem Pirzil and Starchenko. And the setup is the following thing. So in the full generality, let R be any, quote, O minimal expansion of R with like plus and times and less than. So basically, the theorem is like you can include more things than semi-algebraic sets, but like as a special case, it includes semi-algebraic sets. But you can also include crazy things like the real exponential function and like take algebraic sets where I'm now allowed to use the real exponential function and the theorem would still hold true, which is like amazing. Okay, so what is this theorem? The theorem says if I take in our type alpha, which is unbounded, then there exists a non-trivial subgroup of R to the n, such that if I pointwise add the subgroup, so this is considered as constant sequences, I add them to all the sequences in the type, then you end up not getting too far away from the type. It turns out that this is contained in alpha plus mu to the n. So intuitively speaking, this is like saying that this point at infinity was modeled by a sequence of points along this branch of the hyperbola. And like, if I add a constant vector, if I like translate the sequence of points by like a constant amount in the horizontal direction, then the sequence of points was still very close to the hyperbola. And how close the sequence of points remains to the hyperbola approaches zero as you go farther along the hyperbola. So that's what this like fancy model theoretic statement is saying, is that you basically always have a direction under which you're stable under addition up to like a very small perturbation at infinity. Okay, so then how does this apply here? So remember, we get this union of these types. And because we're taking the standard part, which is like the set of limits, this is stable under adding this these sequences that converge to zero, these infinitesimals. So if I rephrase this as h plus alpha plus mu to the n is equal to alpha plus mu to the n, then we get this very nice fact that I have alpha plus mu to the n here. So it's a union of things which are stable under addition by this by a subgroup, where the subgroup depends on alpha. So each like limit as you go to infinity, there's like a different direction that you're stable under. And now because these are constant sequences, I can pull it out. Union alpha of h alpha plus this standard part of alpha plus w plus mu to the n, I guess. To the n. And this is a bunch of lines. Okay. So that's basically what's happening. So the model theorists have come up with this great framework in which this theorem is true, which basically says that you can like partition behaviors at infinity of a set in like a well-defined way, so that each of those behaviors at infinity is stable under adding a different stable under adding some direction. And so the contribution of that particular set of like limits at infinity that are stable under a particular direction, those are going to contribute in the original set an entire line. So for example, that's why, we have this hyperbola up here. As we go to infinity here, it like looks more and more like a set that's stable under a line. So in the limit, it's going to be the line. So that's how these lines end up showing up. And it's entirely a property of like the set having well-defined asymptotics, which it turns out is like a true and much bigger generality. So I'll make some final two notes. So the first thing is that this also works for arbitrary definable groups G. So this specific last thing that I said that I think is the interesting thing. So to get this like more refined characterization that like actually use like the lattice, and you got finitely many parametrized subtori with like lower dimensional sets, you need to do some work. But if you do just this statement, this works for arbitrary definable groups. Definable meaning that I can like write down equations and inequations using using addition, multiplication, and the less than symbol, like GLN, O of n, just any classical group, they all fall under this. This theorem of Pirzil-Sturchenko still holds, which is really great. It also works for arbitrary definable groups. And they're also, I guess, they're like more refined questions that you can ask about like, can I describe, for example, not just the image of X under this quotient map, but can I like describe the distribution that the set induces in the image of the quotient map by like integrating functions that are, I guess, like periodic with respect to the quotient map on like larger and larger subsets of X. And this is like known for nil manifolds, and this is open in general. So I guess that's like an open question. How do these results extend to like measure to distributional convergences, rather than just like knowing what the image of the set is literally, like how fast does like the basically like how fast does the set approach the image as you like intersect X with larger and larger balls, take the projection, like can I describe like what those induced measures are. Okay, so I'll stop there, and if you have questions, I can take questions.
Okay, thank you very much for your talk. Let's thank the speaker first. Are there any questions?
Yeah, I just have a couple of small questions. So given a particular X, like let's say you're given an actual like curve or something, do you have an idea of like what the yi should be, or is it just like this exists?
Yeah, so for a curve, the yi's are just going to be points because they're going to be lower dimensional. And you can write it down in terms of the like if I give you a if I parameterize that branch with like with like a Puiseux series, then you can write it down. And actually, this pair of authors, Din and Vu, actually did that. And for curves, they also got this measure theoretic statement in the full generality of like what happens when you integrate the function on larger and larger subsets. So you can write it down in terms of the Puiseux series is the answer.
Okay, so in higher dimensions, is this just like arbitrarily bad, or like
in higher dimensions is arbitrarily bad? In some sense, no.
Okay.
Yeah, okay, so it's the proof is like effective in the sense that you can actually, for algebraic sets, you could actually theoretically trace through everything.
Okay, yeah, this was the actual question, but yes.
Yes, basically you need to like figure out what the limiting behaviors are. You need to encode that as some subset of a Grassmannian, basically saying like what are the d-dimensional asymptotic behaviors. And there's like well-defined algebraic, there's like an algebraic way you can associate your original variety to the subset of the Grassmannian, and then from that subset you can like extract what these sets are. But at some point, to get this finite union of tori, like something cheeky happens where you basically need to use like the bare category theorem. So what happens is you can imagine that my asymptotic behaviors ended up being like I had like a one-dimensional family of like lines with like varying slope. Then like in that r to the 2 mod z to the 2 example, in like r to the n mod z to the n, let's say I had some set where I ended up with asymptotic behaviors that corresponded to like lines of every possible slope. Then what you're going to see is at every rational slope, you're going to get this nice subtori. At like irrational slopes, you're going to get like this thing that densely fills up. And basically at some point you need to like reduce this countable number of possibilities of what like asymptotic behaviors actually contribute to the closure to a finite number. And then that's I wouldn't say that's the most effective procedure. It does
Okay.
use the bare
You
category.
don't have to use bare categories, right? I mean, as long as your slope is like exponentially undefinable, you also get this kind of explicitly. That's kind of the point of these Shanwell type results, that you can make this explicit. Right? There's this theorem of Ax and of Wilkie that you don't actually have to use bare category. You basically look at the numbers that are not only algebraic but definable in an exponential, right? In the exponential extension of the real of Q bar, and then you also get it. So in a kind of explicit way. That's actually I wanted to ask. So one of the reasons that people are interested in, I mean, okay, so there are the equidistribution results that more additive combinatorics are interested in, and the other one is usually it comes from, I mean, it's kind of surrounding the Shanwell type conjecture, right? Is that somehow, is this topological version in any way, does it have applications?
To the Shanwell type conjectures. Yes. Well, it should. So, example of where this like would be relevant in the framework of Shanwell type conjectures would be something like the exponential algebraic closedness conjecture. So this is a big conjecture from back in the early 2000s, which basically says, given a system of complex polynomial equations, f1 of x1 through xn, e to the x1 through e to the xn, fn of x1 through xn, e to the x1 through e to the xn. When does this, I guess, k? What are sufficient conditions? Are sufficient conditions for this to have a solution? And like sufficient in terms of like, basically like it's going to be some condition on the algebraic variety that f1 through fk cut out in 2n variables. And basically it's going to say that you didn't set up your system of equations to create an explicit contradiction, either by like having it not true for dimension reasons. Like it could be that like you wouldn't expect there to be a solution because, you know, because there just aren't enough parameters.
So these are algebraic, these are the fi are polynomial equations over defined over Q, or what?
Yeah, these are over these are complex, so over, let's see. So there's like a conjecture that the only conditions you need on f1 through fk to have a solution are that you don't end up creating a situation where like a subset of the parameters under some like coordinate change ends up being like overdetermined. So you avoid overdeterminedness, and you also have to avoid a silly thing that can happen, which is like you have to avoid doing something like this. So there's this condition called freeness, which says that we accept that there are some, you know, relationships between exponentials and algebraic conditions that would allow you to create trivial contradictions, and you basically just require that your subvariety isn't contained inside anything corresponding to like a system of equations like this, which would just create a trivial contradiction. And if this were true, it would imply Zilber's conjecture that the definable sets in the complex numbers with 0, plus, times, and exp are all countable, or co-countable. So that would be a very nice application of this. So understanding the like closure of exp is like part way to understanding solutions to polynomial equations involving exp, because it like basically tells you like what things you can, like it tells you about approximate solutions to systems of equations of this type. That's that.
Okay. Any other questions?
Well, it doesn't seem to be the case. I will stop the recording first.